When winter comes to Titan's poles, it brings seasonal downpours of toxic molecules that could, under the right conditions, assemble themselves into structures like the biological membranes that encase living cells on Earth. Called vinyl cyanide, those molecules are created high in Titan's atmosphere, and now, scientists know there is a truckload of them tucked into the moon's orange haze that probably rained down on its icy surface. More than 10 billion tons of it could be floating in Ligeia Mare, the second largest lake in the north, according to the paper published today in Science Advances. What the compound does once it gets into Titan's lakes, and whether it actually self-assembles, is still a mystery. But based on the molecule's hypothesized ability to form membranes, the discovery raises the question of whether one of life's key requirements might be easily achievable in Titan's alien oceans. Crashing into Saturn. This Cassini mission is the most epic yet. In this stunning animation, watch NASA's Cassini spacecraft begin the last chapter of its 20-year mission to Saturn. Titan has unique and weird chemistry, and all the evidence we have so far suggests there's a possibility for it to be doing a lot of things we think are necessary for life to exist, says Johns Hopkins University's Sarah Horst. Everything we have ever learned from planetary science tells us that other worlds are way more creative than we are. The largest of Saturn's moons has intrigued astrobiologists for decades. Titan is more or less Earth-like except for its completely different chemistry. It's the only other world in the solar system where liquids stream and surge across the surface, it clings to a puffy nitrogen atmosphere, and it's literally covered in complex organic compounds. But temperatures on Titan plunge so low, 290 degrees Fahrenheit, that water is hard as rock, so liquid ethane and methane flow into its seas instead. The dunes near its equator aren't made of sand but of frozen plastics, and it rains compounds normally synthesized in chemical processing plants on Earth. There is nowhere else in the entire solar system that has those liquid hydrocarbon lakes, says study co-author Connor Nixon of NASA's Goddard Space Flight Center. You need a whole new biology to support that. A colorized mosaic from NASA's Cassini spacecraft reveals the lakes and seas of hydrocarbons that decorate Titan's northern hemisphere. Image by NASA, JPL Caltech, SE, USGS. Since 2004, the Cassini spacecraft has been buzzing around the Saturn system and helping scientists study this big, weird moon. More than a decade ago, it spied evidence for a molecule with the atomic ingredients of vinyl cyanide, 3 carbons, 3 hydrogens, and a nitrogen, but Cassini data couldn't tell scientists anything about whether those atoms were arranged in the vinyl cyanide configuration. More recently, study leader Maureen Palmer, also currently at NASA, and her colleagues took a look at some data gathered by a cluster of telescopes in Chile called ALMA. Scientists staring at cosmic wonders such as distant galaxies and interstellar clouds had been aiming ALMA's dishes at Titan and using the hazy world to calibrate their observations. As it turned out, the unmistakable signature of vinyl cyanide, not just the right atoms, but the entire molecular structure, lay in calibration data taken between February and May 2014. Using those serendipitous data, the scientists determined that millions of pounds of vinyl cyanide hover in Titan's atmosphere. The team detected it primarily at altitudes above 120 miles, which makes sense, because vinyl cyanide forms when sunlight and other charged particles strike the top of Titan's nitrogenous sheath, busting up the existing methane and nitrogen like Lego blocks, Nixon says. Those atoms then reassemble into a variety of complex structures, including vinyl cyanide, which slowly condense and sink through the atmosphere, eventually hitching a ride to the surface in raindrops. Because of Titan's seasons and atmospheric circulation patterns, the highest concentrations of those molecules rain down upon whichever of the moon's 2 poles is wrapped in winter, but showers of these intriguing particles sprinkle the entire ice world to an extent. It could be coming down all over Titan and just lying on the surface as an organic residue. It could be reactive and making long-chain polymers, Nixon says. Or, it could be dropping into the lakes, and once it's in the lakes, it self-organizes. The idea that vinyl cyanide might form something similar to earthly cells comes from a research group at Cornell University. That team looked at about a dozen of Titan's atmospheric molecules and used computer models to determine which of them had the ability to self-assemble into membrane-like structures called azotosomes. Helmed by then graduate student James Stevenson, the team found that vinyl cyanide had the best chance of forming something that could be astrobiologically relevant in Titan's extremely cold, liquid methane seas. Like earthy membranes, the simulated configuration was both strong and flexible, possibly forming a hollow sphere capable of sequestering other ingredients necessary for life, and its tendencies to aggregate or separate in methane were just right. The molecules have to like each other, not so much that they clump together with no space in between, but also like each other enough that they'll form chains, and then if the ends come near each other they say, "Oh yes, let's link up," says Cornell's Paulette Clancy. So far, no one has done the actual lab experiment needed to prove vinyl cyanide can form membranes. It's difficult working with cryogenic methane and poisonous cyanide, and after all, there's only so much you can do to replicate what's happening on Titan when you live on Earth. Find the best organic chemist you can find, and ask them if they're up for the challenge, Clancy says. Still, the fact that vinyl cyanide has the theorized ability to form membranous balls is even more tantalizing now that we know how abundant it is on Titan. Going by mass alone, there's enough of it in Ligeia to make at least 36 billion giant squid. The discovery might be the extra kick needed to send another spacecraft diving toward this strange orange moon. We still are at the very beginning of the experimental work that's really necessary to understand Titan's lakes, Horst says. But we're never going to fundamentally know what the system is doing until we're able to go back